Today is review day, review for exam day. So today, I'm just going to tell you what you can bring to the exam, what to expect on the exam, and then the rest of the class, is any kind of questions you want to ask, I will give you the answers to any question you want. And we'll go through it. So, exam 1, no calculators. No calculators. Period. End of sentence. No more calculators. Something is wrong with the way my tablet is working. So there will be math. You will be required to do math. However, yeah, that's fine. No calculators. It's going to be basic arithmetic, maybe addition, division. So things that we're covering, chapters 1 through 3. I'm winded after that dance. That's a little. Chapters 1 through 3. That includes things like number systems. That includes truth tables. That includes Boolean algebra. It's actually in the most recent edition of IEEE Spectrum, they had a little puzzle section, and in it, they reminded me of my favorite law. What's my favorite law?
The Morgan's Law.
The Morgan's Law. It was named after a real person, but I never remember. It's Augustus de Morgan. That's interesting. Boolean algebra. And then probably the most interesting topic is K-maps. That was also named after a real person, Carnot. Don't know his first name. I'll have to wait till the next IEEE Spectrum comes out with a puzzle for him. In terms that most of you have never had a class with me, you don't kind of know how my exams roll out. It is usually mostly short answers. Think Die Hard, sort of fill in the blank questions. Alan Rickman, Die Hard. Mr. Takagi. Short answers with a few long form problems. Long form in this case is probably a ridiculous K-map. Short answers are reduce or tell me a little bit about something or convert something from one base to another. I do aim for these to be about 50 minutes. Some years I'm more successful than others. Okay. But when I say I expect you to take you 50 minutes, that means that you can do number system conversions at the speed at which I mentioned earlier. Okay. So if you haven't been practicing your number systems, or if you haven't memorized those first 15 numbers, how many people have been using your flashcards? Well, I do have the names of the people who made flashcards, so you'll get those extra points. But those extra points will be worthless if you didn't use the flashcards, because it's gonna be hard. Let me just underline this one more time. No calculators. Okay. You can bring one page single. No. I was in a good mood because of the dance, but then you guys didn't use your flashcards. No. You've been using them. Well, so that's out of 50 people, one person, so 2% of the class. I was going to give you a 1 page, so you can have 2% of 1 page, which is about the size of your thumbnail.
I can make it.
No magnifying glasses. All right. Anyway, no, you don't need a cheat sheet for this. Okay? You can derive the first 16 numbers. The way it will work is there will be assigned seating. I'll have a seating chart up here. You'll either be in here or in 214. There'll also be a seating chart over in 214. So depending on where you're set up, you can figure it out. There'll be one of the TAs in each room, and then I'll go back and forth between each rooms. The TAs will have instructions that they know nothing about Boolean algebra, nothing about 260. If you have a question on what the question is asking, they will be able to answer that. But in terms of how to do something, they have no clue at this point. They have intentional amnesia. So that's it. Those are the topics. This is a fairly straightforward exam because it's just number systems and Boolean algebra, simplifying equations. Rest of the class is yours. We've got 45 minutes to talk about whatever you want.
With some number systems, is it just going to be the core biggest ones? Or is it going to be?
I mean, remember this thing that I did where I was like, all these number systems to here, to here, to there, to there, to there, to there, to here, to here.
Can I expect to see like base 10 to base 7?
You might. I mean, number systems as a concept is pretty reasonable. You should know how to go from any base n to base 10 and how to go from any base 10 to base n. You should understand what's happening. So yeah, there's a possibility that I might give you just some random number system. In fact, probably higher than likely average. Does anybody want to do a problem like that? Or? Sure. All right, let me, just so that I don't waste your time, I'm going to use a calculator because arithmetic for me is tough. So let's just, let's make up some numbers. 423.28. Base 10 is what in base 5? What is it in base 5? How do we do that? If you're going from base 10 to any other base, what do you have to do? Divide. So we start with 428, and we divide it by 5. And 428 divided by 5 is 85.6. That's what happens when you type it into a calculator. That's unhelpful. 85 times 5 is, of course, 425. So that leaves a remainder of 3. 85 divided by 5 is 17 even, meaning a remainder of 0. At this point, I think I can eschew the calculator. What's 17 divided by 5? 3 with a remainder of 2. What is 3 divided by 5? 0 with a remainder of 3. And that's the important one. When you reach 0 as the quotient, you're done. And then you read bottom to top. So 3203 base 5 is equal to 428 base 10. Now you're on an exam. How do you know if that is correct? Well, the quickest way to do that is to convert this back into base 10 and see if you come up with the same number. So let's do that. We can always check our answer. That's why this is actually pretty simple. We can always check our answer. 3203 base 5, all we have to do is write down all the powers of 5. So this is the 1's place, the 5's place. What's the next place? The 25's and the place after that. The 125 place. So we'll take 3 times 1, 0 times 25. No, 0 times 5. 2 times 25. 3 times 125. So 3 times 1 is 3. That's 0. 2 times 25 is 50. 3 times 125 is 375. So 5 plus 3 is 8. No carry. 5 plus 7 is 2. Carry the 1. 428. The fact that these two things match means we've done it correctly. Okay? And that covers going from base 10 to base n, and from n to base 10. N being whatever number you choose. Let's do one more with 428. 428 base 10 to base 20. Base 20. How do we do that? Yeah, 428 divided by 20. I don't know if I'm going to get anything good out of this. I was hoping I would, but. So that's 21.4, or 21 times 20 is 420. So that's a remainder of 8. 21 divided by 20 is 1 with a remainder of 1. 20 divided by 1, or 1 divided by 20 is 0 with a remainder of 1. So it's equal to 118 base 20. And you're always going to see that when you go from a small base to a larger base, the magnitude, the apparent magnitude of the number is going to go down. Okay? Because each place means more, so you need less overall. So 428 goes down to about 118 as a number. But the 100 in base 20 is 20 to the 2. I think 400, right? Yeah, 400. So that 1 is worth 400 all by itself. Okay. Other questions?
You mentioned a ridiculous K-map. How ridiculous is that?
I mean, not that it would be a ridiculous K-map. The largest K-map I would ever give you is a 4x4. But I might ask you something with lots of don't cares or many different ways to solve it. Or I might ask you for a product of sum and then factor it and then decompose it. And you know, so it would be a longer, more involved problem. Closer to a real world problem where I give you just a word problem, blah, blah, blah. Kind of like the lab, if A is 1 and B is 0, or if this is true or this is true. And then you would have to build your truth table, the K-map, and then implement it using NAND gates. That kind of a long problem. Each one of those steps all by itself isn't too bad, but just putting them all together in a timely fashion, that would be the part of that would be the test. Can you do it in a timely fashion? Yes?
Did you do simplifying some of the Boolean algebraic equations from 3.6 and off? Maybe a couple of those.
Yeah, you want to give me a specific example?
Oh, I got 2.
You've got 2.
Awesome.
I mean, I've got a book, I think.
Oh.
So, yeah, which one? Yeah, this is fine. If you guys want to do a particular problem, give me a page number here. 119. Okay, 119, what number? 3.8C. That's roughly warp 2 in the TNG universe. C, W, Y, Z, or Y bar Z, Y bar X bar, or W, X, Z bar. And what is it actually? Find the min terms of the following expressions by plotting each function in a map. Okay. So it wants min terms. So first thing, how many variables are there? There are 4 different literals. There's W, X, Y, Z. So here's my K-map. And this is asking this isn't necessarily the only way to solve this problem, but what it asks us is fill in the K-map based on this equation. Now remember, I gave you rules that say, I'm sure I would have come to it eventually. Thank you. I was already planning the next part of the talk here. 1110. Yeah, it'll totally screw you up if you do that. I gave you rules that say if you have a group or a number of cells, if it's 16, that's just equal to true. If it's 8, that's 1 literal. If it's 4, it's 2 literals. If it's 2, it's 3 literals. And if it's 1, it's going to be all 4 literals. So right off the bat, I know that the fact that I have 3 literals here means this is going to be 2 cells. This is only 2 literals, so it's going to be 4 cells. And then this is also going to be 2 cells. So each of these corresponds to 2 cells on this K-map. So let's just go in order. W, Y, Z. This term means there's going to be a 1 any place where W is 1, and Y is 1, and Z is 1. So let's just look at this. Where is W1? Well, W is 1, or W is true, right there. Y is true here, because this is Y. Y is the first literal there. And Z, where is Z true? Z is true in the middle. So there's Z. So what do we have? We have W is true, Y is true, Z is true. So where is the intersection of this? Here's W in these bottom 2 rows. Here's Z in these 2 rows. So we're down to just this box. And finally, Y also has to be true. So the final min term is these 2 cells. So what are the min terms associated with these 2 cells? If I was writing sum of min terms, what is this cell here? It's 15. The only way to do it is just read off. 1, 1, 1, 1. That's 15. What about this cell down here? 1, 0, 1, 1. That's 11. 8 plus 2 is 10 plus 1 is 11. So there's the first term. And it's got 2 cells in it. Next is W bar. Well, W bar is here. And X bar. X bar is the top and the bottom. So the 4 cells that meet that criteria nope, hold on, back that up. Where X is false, X being, or let's start with W bar. W bar is any of these 8 cells. X bar is the top and the bottom row. But since we don't have anything in the bottom row, we're limited to just the top row. So this group of 4 top cells is our min term. So what are these min terms? We can write them out. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. So what are those?
0, 1, 3.
Yes, 0, 1, 2, 3. Doesn't matter what order we put them in the expression. Okay, only matters that we fill them in correctly in the K-map. So that's 4 cells. Great, great. And then the last one, what color haven't I used? Yellow. WXZ bar. Well, we know where W is. It's these 8 cells. We know where X is. X is the middle 2 cells. So already we've got a bit of a Venn diagram here. We're only worried about these middle 4. And finally, Z bar. Now, Z bar is this cell, or this column and this column. So we limited it to 4 cells. So our final implicant is where those 2 intersect. Those 2 columns in that middle row. So what is the leftmost cell? That's 1, 1, 0, 0, or 12. And this cell here is 1, 1, 1, 0, or 14. So all told, if you were to fill this out, this would be 0, 1, 2, 3, 11, 12, 14, 15. Find the minterms of the following Boolean expressions by first plotting each function in a map. All right. Now that got kind of messy in there. You didn't have to draw big boxes over everything, but illustratively, I think that was good. How was that? You want to try another one of these? You said you had 2, I remember. 3.9b. Okay, 3.9b says f of a, b, c, d is equal to sum of minterms 0, 2, 3, 5, 7, 8, 10, 11, 14, 15. 0, 2, 3, 5, 7, 8, 10, 11, 14, 15. And 3.9 says find all of the prime implicants for the following Boolean functions, determine which are essential. Okay. Well, here we go. We start off with a K-map. Being very nice straight lines here today. Okay. And then I go back to my pen here. So we have A, B, C, D. It's important to always use the same order because 0 implies A naught, B naught, C naught, D naught in that order. So then 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So we have to fill this in. So filling it in, 0, 1, 2, 3, 4 is nothing, 5, 6, 7, 8 is down at the bottom row, 9, 10, 11, 12, 13, 14, 15. And it wants us to find all of the prime implicants. So first thing we do is set up our checklist. 16, 8, 4, 2, 1. Obviously, we don't have 16. Do we have any groups of 8? No. So now we're down to groups of 4. First, this is the obvious group of 4. Okay. Now we're looking for all prime implicants, not just ones that'll simplify. So what other groups of 4 are there? There's one more obvious one. The square one right here, yeah. And then we have to remember that K-maps actually form not just a tube, but a torus in the back. The corners, yes. Okay. Are there any other groups of 4? Wrong. The bottom 2 and the top 2. Yes, it's completely superfluous to circle this if you're just simplifying. But if you're finding all of the prime implicants, it's a group of 4. Got to do it. All right, now before I make a fool of myself and move on, this looks group of 4, group of 4, group of 4. I don't see any other groups of 4. Anybody want to be a hot shot and show me if there are other? Okay, I don't see it. So now we're done with 4. Are all of the ones circled? No, so we got to keep looking for groups of 2. So groups of 2 that are not already covered by a larger implicant. Remember, prime implicant means it's the biggest group that you can circle. So this is not a prime implicant. Even though we have to go and look for groups of 2, we're looking for groups of 2 that have at least one thing that's uncircled. So that is not a group of 2. I'll get rid of that. So where's their group of 2? Yeah, the one that isn't covered. Now everything is circled, so we're done. We're done at 2. So the question is, which of these circles are essential prime implicants. What does it mean to be an essential prime implicant?
At least one uncovered one.
There has to be at least one cell that is not covered by any other prime implicant. So we just went through and found all the prime implicants. Let's just star the cells that don't have more than one prime implicant circling it. This is a great candidate. That's a great candidate. This is a great candidate. That cell is covered by two things, two things, two things, two things. Ooh, this one is only covered by one thing. This is covered by 3 and 3. So I've starred 4 cells. What are the implicants? So this is the corners, and the corners are equivalent to B bar. Hold on. Let's not jump ahead of ourselves, and let's go to a real color. The 4 colors, B bar ANDed with D bar. That covers actually 2 of those cells. What about this one in the corner? That's going to be A, C. Finally, this guy. Even though he's smaller than the rest of the prime implicants, he's still a prime implicant because he is the largest contiguous implicant that is not covered by any other. So that is going to be A bar B D. So that, I think that find all the prime implicants for the following Boolean functions, determine which are essential. That is actually not what the question asks. The question asks, find all of the prime implicants. So these are the essential primes. Let's list off all of the prime implicants. First off, the corners are a prime implicant. They're also essential, but they are a prime implicant. Let's look as I'm going across. The vertical one, that's CD. That is a prime implicant, but it is not essential. What else? Then we have the top and the bottom half. That's B bar C. Top and bottom half. We have the bottom corner, which is A, C. And we have the group in the middle, that's A bar, B, D. So I have 1, 2, 3, 4, 5 circles, 5 prime implicants. Only BD, AC, and A bar, BD are essential. So it says find all prime implicants. There they are on the left. Only the ones that are on the right, or the ones that I've started with a yellow dot, are essential. Okay? Yes?
Why did you include an A and BD?
Why didn't I? Say it again, please, louder.
Why didn't you include an A and BD?
N-A.
Yeah, A. That A. These are 2 top ones.
This guy here?
Left one and
Here and here? I made it into 4 corners. That's better than doing 2 corners. Okay? So again, that would be an example of an implicant, but it's not a prime implicant. It's not an essential prime implicant. Yes, you can circle these 2 because they are connected. But remember, if you look up from this cell, you hit this cell. So if you actually wrap this around into a tube and then into a torus, all 4 of these form a square block. So it's better to do that. And that is B naught, D naught. Algebraically, if you were to circle these 2, what did you come up with? A bar, B bar, D bar. It's under my face. You would have come up with that for these 2 corners. Then the other corner, other bottom 2 corners here, would have been A, B bar, D bar. Well, B bar, D bar is common to both of those terms. Factor them out. You got B bar, D bar, And what's left? A bar or A. That's 1. 1 ended with B bar, D bar is just B bar, D bar. Okay. So again, K-maps are just doing the algebra for you. All right. Yes?
Why didn't you include the box on the third from the left on the top?
The column?
Yeah. Well, the 3 midterm box. Because you have all the corners and then the bottom box and then the 2 in the kind of.
So give me the midterm. You're talking about midterm 3 here?
Yeah.
Why did I not include that in? Because it's not essential. Even though you need it to fully simplify, this is not the answer to F, A, B, C, D. It's only the essentials. And that's what the question is. It didn't say simplify. It said find the essential ones. If we were to actually circle these, I'm going to circle them in green. So BD takes care of the 4, B naught, D naught takes care of the 4 corners, right? AC takes care of this group of 4, right? So I've got those circled in green. ABD takes care of these. But you're right, this cell has not been included. So in order to simplify, you have to get some implicants, some prime implicants, that are not essential. That's just kind of a definition thing. To simplify, you need to circle all the ones. But before you circle anything that isn't essential, you have to circle all the essential prime implicants. So the first step is find the essential prime implicants. Okay? And then, yes, you are correct. This cell hasn't been circled. So you need to choose. Do you choose the vertical guy, which would be CD? Do you choose the top and bottom 4, which would give you B bar C? All right? You would have to choose one of those 2, but not both. Right? You would only need to do 1. And in terms of minimizing your overlap, they both overlap 3 cells, so not really a big deal either way. But that question wasn't asking us to simplify. It was saying just find the essential prime implicants, which is a step along the way to simplification. Okay? That's a good point that she made. We didn't simplify this. We just found the essential primes. We still have to circle at least one of the non-essential prime implicants to simplify this. Okay? That was a good problem. I like that one. What else can we do? 3-11. 3-11. 3-11. F of x, y, z equals sum of minterms 0, 1, 2, 5, 8, 10, 13. What is it asking you to do with it? Convert the following Boolean function from a sum of products form to a simplified product of sums form. Okay, so we're looking for a K-map. We know that it's going to be 2 by 4 because we only have 3 variables. We label it x, y, z, 0, 0, 0, 1, 1, 1, 1, 0. Wait a minute. What?
Yeah, that's where I got confused.
All right, so Occam's razor. The simplest explanation is they forgot to type a W.
Yeah.
All right. That's okay. So this is going to have to be W X Y Z. That makes the fewest assumptions, the fewest number of typos to make this make sense. Because otherwise, you wouldn't have a midterm 8, 10, and 13. So either they made 3 really big typos or just 1 typo of omission. So, all right. So we have to relabel this a little bit. Make it a little bigger. Okay. Those crafty devils. 0, 0, 0, 1, 1, 1, 1, 0. Okay. So it's a W. W, X, Y, Z. All right, now we fill these in. 0, 1, 2, no 3, no 4, 5, no 6, no 7, 8, which is again down in the bottom corner. Never forget that. No 9, 10, no 11, no 12, 13, no 14, no 15. It wants a product of sum implementation. To find product of sums, we start by finding F naught. F naught means we circle the zeros. So, where do we start? If we don't know where to start, we can start by just finding all the prime implicants, just like we did on the last problem. But I'm gonna see what I can do. I'm gonna take those 4. I'm gonna take these 4. There's no overlap there. And then I'm left with this guy. And really, I don't see a whole lot of options for him. I think you gotta just do that. Okay, there is another prime implicant. The prime implicant that I didn't circle is this group of 4. But obviously, he's useless because he's covered by, all 4 cells are covered by something else. So F bar, if we solve for him, is going to be W, X, Y, Z. That's, I'm doing the one that's the side in the middle vertically. That's W. That's not a W that I wrote. Oh, because it is X. It's X, Z bar. Yeah, we're in the Z bar columns and the X positive columns. The vertical column is, of course, Y, Z. And finally, this guy down here is W, X bar, Z. Now, that is still a sum of products representation, but it's a sum of products representation of F bar. So, invert both sides. If you invert F bar, you're back at F. F now equals X, Z bar, NANDed together, ANDed with Y, Z, NAND. ANDed with W, X bar, Z, NANDed together. Which is still not enough. It's still, there's not even a sum in here anymore. So we continue applying my favorite law, X bar or Z, ANDed with Y bar or Z bar, ANDed with W bar or X or Z bar. And there we go. That's it. That's all they wanted you to do for that. So aside from the fact that there was a typo right there, fairly straightforward. Okay. What else? Yes. 3.1a. 3.18? Do you mean 3.18? Oh, I was looking at 3.1. I'm like, those aren't numbered. Those are lettered. 3.18. Yeah. Oh. Okay. 18. F of A, B, C, D equals A exclusive or B, exclusive nor B, ANDed with C exclusive or D. Draw a logic diagram using only 2 input NOR gates to implement the following function. Okay. So first thing to understand is exclusive OR, X exclusive OR Y, is the same as saying X Y bar or X bar Y. Whatever those two things are. Now, we've done universal NAND gate. We did that in lab. NOR is also universal. You can build everything out of a NOR gate. So maybe that's where we start. Can we build an inverter out of a NOR? Well, let's write the NOR truth table. XY NOR 000111011. NOR is not OR. 1000. So right off the bat, I'm looking for something where if I tie one input high or low, I get an inverter on the other input. And I see that if I take a NOR gate and I tie one input low, if I put in X, I get out X bar. I even see that if I tie the inputs together, that's also an inverter. Well, now we're well on our way, because if we can make an inverter out of a NOR gate, how do we make an OR gate using only inverters? Yeah, you take a NOR gate, and then you stick a NOR gate with its inputs tied together on the output, and then you've got X, Y, X, O, that's not an OR, X, or Y. All right, and if we can build an OR gate, we can build an inverter, an AND gate. Well, an AND gate is an OR gate with both of its inputs inverted. So we know how to build an OR gate because we take a NOR gate and then another NOR gate, tie the inputs together. Then we've just got to put inverters here. So this, collectively, is an OR gate. Oh, actually, hold on. I take it back. We actually don't. That becomes, there we go. In AND, yes. Yes. That's a NOR. Sorry, I just started with the wrong picture. So there we go. No, wait a minute. Oh. Only one thing to do. Whoop. That was not the thing. That was not the thing I wanted to do. Let me just start that over again. An AND gate, applying De Morgan's law, would be OR gate, both of its inputs inverted. That's a NAND gate, right? An OR with both its inputs is inverted is a NAND. So if you did a NOR with inverted inputs, that's an AND. So actually I had one extra NOR. You just take a NOR and then two NOR gates on the input. I got carried away. And then this is tied together. That's tied together. Boom, boom. X, Y. So now we have an inverter, an AND, and an OR. So this, it's a bit of a longer function, but we can do it because what we need is, well, let's just draw what it would actually be. Exclusive NOR ANDed with exclusive OR. Okay. Now, one of the other things that we know about our rules of exclusive OR is this is the same as A exclusive OR B bar. That was one of our rules of Boolean algebra. So to make this a little bit simpler, let's take this and make it an exclusive OR with an inverter. So we've got A, B, C, D, and an AND gate. So I know at the very end of this, I need to build an AND gate out of only OR gates. Now, for clarity, I'm just going to draw inverters because it's just a NOR gate with its inputs tied together. So there's my AND gate. Then I need an exclusive OR. And we know that exclusive OR is nothing more than an OR gate so that's a NOR with an inverter on the end of it. And then those each go to two AND gates. And. And then we have each of these is an inverter. And an inverter here. A, B, A, B. Although, since here we've inverted B, this is really going to be one more inverter. As long as you keep at this, you keep your head on straight. There's B. And there's B. Now, obviously, some of this is going to simplify, right? Okay. So then we got to do down at the bottom. This one's the easier one because there's none of that shenanigans there. Maybe it might have been easier if I had left it as NOR. I could have just had one more inverter at the end. But that's a design decision. You can try it both ways. So that's C, D, and then C bar, D. Well, so what reduces now? What reduces? Any place you see two inverters in place, you can get rid of those. So there. Or else. I guess that's it. So all told, let's bring this over to the next page here. Control C. Control V. Our next step is just to start writing it out. So NOR, go into two NORs. Oh, I left this as an AND. I left that as an AND. AND by itself is NORs with inverted inputs. Oh, goodness. So each of these is a NOR with inverted inputs. And then that goes to A, B, and then this one has an extra set of inverters, so I'm just going to erase those now. A, B, which is exactly what you'd expect, right? A and B are both 0 or they're both 1. That's what an exclusive NOR means. And then up here, these are AND gates, so I need an inverter here and an inverter here, an inverter here, and inverter here. But then remember that I invert one of each. So this is CD, this is CD. So at the end of the day, these two go away. And we're left back with C inverted, D inverted. So there it is. There is A exclusive NOR B ANDed with C exclusive OR D. Just a big cascade of NORs for the most part. Now, it didn't even give us the option but we could have started to combine some of these into larger gate pairs. I guess that means we're out of time. All right. So I will see you on Monday for the exam, bright and early. Have a good weekend.
You still at 6 though.
No.